Yeah, cool. All right. So yeah, welcome to the last workshop of beginner track. Um, so just a quick reminder that this workshop will be repeated next quarter as well. Um, okay, I guess yeah, Vaishnavi has something to say about next quarter's track, so take it away.
Yeah, thank you. Hi everyone, I'm Vaishnavi. I'm Workshops Director of ACM, and I wanted to jump in really quick for our final workshop of the quarter to talk about some of the tracks we'll be offering next quarter. Like Adithya was saying, we are offering beginner track again. So if you ever want to just come by, review some of the concepts, or if you think your friends would really enjoy it, please let them know that beginner track will be offered again in the winter. It will be taught by different officers. I think the track that you guys would find most useful is advanced track. It picks up right where beginner leaves off. You review linear and logistic regression, and then you start delving into neural networks and different algorithms that are really cool and really useful in machine learning today. So if you want to continue on this ML journey through ACM AI workshops, do check out Advanced Track in the winter. And we're also offering a third track, Advanced Plus Plus, which just delves into more complicated deep learning models. And each week we'll be talking about a different model, and that track is more conversational too. So if there's a specific model that you want to learn about, then the content is also very flexible, and officers can accommodate that. With that being said, you can attend advanced track next quarter and advanced plus plus. It's really up to your interests. We'll be going over all of this in much more detail at our general meeting in the winter, but just keep that in mind, going into winter quarter, and we hope to see you next quarter. And one more thing, thank you so much for being out here, out of workshops in the middle of week 9. We really appreciate that. And I think Sudhanshu, Jenson, and Adithya will agree that we really appreciate your turnout in this virtual setting. Yeah, please make sure to fill out the feedback form. We would really appreciate that. This is the first time we're offering this in a virtual setting. So next quarter, we can take that feedback and put on better workshops. Thank you.
Yeah, all right. Yeah, so yeah, as Vaishnavi said, we're super glad you all have made it to our final workshop. It's definitely been a ride. We've had 9 workshops for this quarter for beginner track. So to top it all off, we are today we're gonna do a little bit of yeah. So this is gonna be the last workshop for this quarter. So to answer your question, Cameron. So yeah, so today we're going to do a little bit of review of last workshop, since a lot of y'all weren't able to make it to the last workshop. We're going to do a little bit of review for that, where we kind of implemented linear regression on our own, and then we're also going to delve a little bit into logistic regression. So yeah, head on over to the, let me see. All right. Yeah, so head on over to the form, the Google form, and we'll get started. So, all right. So can everyone see my screen right now?
Yeah.
All right. Cool. So yeah, take your time to fill this out. It really helps us a lot. It helps us kind of know if we're doing what we do well. You'll find the starter code for today's workshop on there, so go ahead, click on that to get started. We're gonna pretty much start from scratch where we left off in the last workshop. So yeah. Cool. So yeah, so for everyone who didn't make it to the last workshop, we kind of went ahead and did a bit of linear regression. We basically learned a line, this one over here, pi x plus 10. We defined a few functions for it, and we also implemented it. But today we're going to look at it a bit more of a real life application. But before we do that, I'm going to quickly go ahead and review the functions we did last time, just so that everyone's on the same footing over here. And if anyone has any questions, feel free to put it in chat, or go ahead and just unmute yourself and speak up. Yeah. All right. So our task is to implement a line pi x plus 10. So we start off by just defining a function that gives us the output value for any given x. Let's see. All right. Do people have? Is there any issue with viewing it? I can zoom into the notebook a little bit if that's what people want, because I think there might be an issue with like just looking at the notebook. I hope this is better for everyone. Let me know if it isn't, and I'll change accordingly. All right, yeah. So our task is to implement the line pi x plus 10. We do that by defining this function np.pi, which taps into the NumPy library, gets the value of pi into some input value x plus 10, and returns that immediately. We want to next step is we want to generate 100 data points between -5 and 5 inclusive. So we do that with this this line over here, and x is essentially going to hold an array of all our input values. We reshape it into a row vector, and as you can see, it now has a shape of 1 by 100, containing 100 linearly spaced values between -5 and 5 inclusive. We call y is equal to f of x, so that means we will essentially get all the output values are labels for all our input values x, and once again that has the same shape as our input values, our input vector, I guess, x, which is going to be 1 by 100. So that's a sort of initial setup phase. We're now going to delve into our hypothesis function. Our hypothesis function, since we're only dealing with one unknown here, it's only going to be a one-dimensional scenario, so we only have x. Therefore, w is just going to be an integer. It's not necessarily going to be a vector, as we've seen during the linear regression like theory workshop, but we're going to take a look at that a little bit more in depth today. So yeah, before we begin, I'll just quickly go ahead and run all the cells. Yeah, everyone, don't forget to do that as well, because once we continue off from where we ended last workshop, things might not work unless you run all the cells before. So don't forget to do that. Cool. All right. So that's our hypothesis function. We want to initialize our weight and bias randomly. So we tap into np numpy is random random.rand, which basically gives us a random value back, a random integer, so to speak, and we define a hypothesis function, which is just wx plus b, which we will call y hat. Yeah. And then once that's over, we will quickly plot both of these. So we've not really introduced you guys to matplotlib, which is the plotting library we're using, but don't worry about that. These are the kind of the functions. I mean, these are kind of the lines you need to essentially just draw out a simple few line graphs. So plotting x comma y. Y's are labeled, x is our input values, and you see this blue line over here, which is essentially pi x plus 10. And once we plot x comma y hat, and passing in our randomly generated weight and bias with our input values, you get this line over here. So as you can see there, it's not the same line as this one over here, which is the one we're trying to learn. But by the time we run our gradient descent, we learn the line, this orange line will overlap with the blue line, which indicates that, yep, we're successful. We've learned the function we want to learn the best we can. So yeah, before I move on, are there any questions till now? Put them in chat. speak out, anything's fine.
I have a quick question. What were the random, um, the random data points for
The
before this?
randomly, so yes, I'm assuming you're talking about X right here. Um,
Yeah, yeah.
yeah, so those are essentially our input values. So we need some number of values we want to input into our function to train it. So you can think of this as essentially the training data. It's a whole bunch of values from -5 to 5 inclusive. Again, the fact that we take 100 data points and the fact that we limit our range to -5 and 5 are arbitrary. We just want to get essentially a set of a whole bunch of points that we can provide to our y hat, our model essentially to train it so that it eventually learns this blue line, which is pi x plus 10. So as you can see initially, the line that we have, random, not really the one we're looking for, but we will use the randomly generated values to train the model so that it'll eventually reach, it'll eventually result in a weight and bias value that are pi and 10 respectively, so that it can basically learn this line. But yeah, X is just essentially our input data, our training data, however you want to refer to it. So yeah.
Okay, thanks.
All right, cool. Okay, so it says, why aren't the data points visible on the scatter plot? Oh, that's because there are 100 data points. We don't need to essentially uh, plot all the points on the graph. It's basically the way Matplotlib works is it's just represented by the lines. It just draws a line through all the points, which results in the blue line we get. So yeah, pretty much, yeah. So as you can remember, we got 100 data points, and showing all of them individually on a graph as small as this would be a little bit of a hassle and not that nice on the eyes. So it just looks like a continuous line because of that. Okay, cool. Well, let's move on. So yeah, we need to also find, we also need to implement a function that is our error function, our loss function. So we do it like this. If you remember right, this is our loss function for linear regression. And we implement that just like this. We call np.average, and then we subtract y hat from y and square that resulting value. So y, as you guys remember, is our label. Y hat is our predictions. We subtract we subtract y hat from y, we square it, and we take the average, which is that 1/n component, to find our mean squared error. So yeah. Okay, yeah. I guess yeah. We'll touch upon the whole np.dot scenario. We want to do this because it's a little, the way NumPy implements matrix multiplication, a little weird. If you want to do conventional matrix multiplication, you need to call this np.dot, which may seem a little weird at first because you would expect dot to represent the dot product, and it's the whole thing. But if you want to multiply two matrices together, you call np.dot on them, just like this. You have np.dot a comma any one matrix comma another matrix, yeah, to multiply them together. If you just do conventional a star b or a asterisk b, that's going to perform an operation called the Hadamard product, which is not very much, which is not matrix multiplication like we need. So yeah, just quickly going over that. Let's see. All right. So now we want to find a function that gets us our gradients. So, so if you remember from linear regression, the theory workshop, these are how you find the gradients for our weights and bias. And as you can see, this is kind of how we implement that in our function here. We first grab n, which is the number of data points that we have, the number of input training samples, and then we have an empty dictionary, and then we kind of apply these. So np dot again, array multiplication, where we multiply y hat minus y into the transpose of x, and then multiply by 2 over n. We do something similar for the bias, and then we just return that dictionary. And to top it all off, we will go ahead and look at gradient descent, which is the big chunk here. So obviously, the gradient descent, we first need our learning rate, which we assign to alpha. And we have losses. We want to keep track of our losses as well. We'll set that to initially an empty array. And then we loop. So our gradient descent will occur in 10 iterations. It's an arbitrary value. It's an arbitrary number. We took 100. You could take different values. The best way to kind of like go about this would be to kind of try gradient descent with a whole bunch of different iterations, but it's an arbitrary choice. So yeah, first step is that we get our predictions. We initially assign WB, which, as you remember, we initialize as random. And so our initial set of predictions is not going to be that great. And then we find our gradients, x comma y, and with our predictions, and we get the dB and dW, which, if you remember, were the gradients over here. And then, as you guys remember, these are the two key equations we use to update our weights and biases. And essentially, this is the shorthand way of doing this in Python. B minus equals alpha into dB, which is essentially B equals B minus alpha into dB. We do the same for weights. And then we find our loss with our predictions and our labels. We call MSE on it, which is our mean squared error function. And we append that value to the losses array. And once all of this is over, we just return WB and our losses. So we expect W after this training process to be essentially pi, or at least close to pi. We expect B to be close to 10, and we expect our losses to be close to 0, the last value for our losses. Because as you guys know, our loss is an array that tracks our loss values over time across all these 100 iterations. So yeah, now all we have to do now is essentially just call gradient descent, which we do with x, y. We set our learning rate to 0.03. And if we try to print out W and B, look at what we get. W, as we expected, should be pi, and it pretty much is. It's close to it. And B is, as you can see, pretty close to 10. So we were successful. Plotting these on a graph, as you can see, these are the same lines we use, same commands we used previously over here. Last time we did it, the orange and blue line way off each other, but this time when we did it on top of each other, which means we've done good stuff. And yeah, also plotting our losses, and as you can see, initially it's pretty high. We expect that when we initialize random weights and biases, but as the gradient descent algorithm kicks in, our losses decrease quickly until essentially gets close to 0. So yeah, that is basically the chunk of linear regression. We did a very simple example last time, but yeah. So we also tried out the gradient descent, calling gradient descent with different values of alpha. which is our learning rate. So we took a smaller value and a larger value of alpha. And as you can see from this graph with these labels here, the smaller learning rate took a bit longer to reach the to minimize our loss. The medium learning rate took its time, but it was quicker than the small learning rate, and the large learning rate crushed it, almost went immediately zero. So yeah, different learning rates result in different a different amount of time taken to learn whatever we're learning. But yeah, note, you can't just simply pop in a really large learning rate, because the issue with that is learning rate like 0.5, for example. We were using 0.1 as our large learning rate in the previous example. We use 0.5, and as you can see, our loss just explodes. That happens because we essentially skip our minimum during the learning process, the training process. So as you can see, initially things are good. Our loss is 0, but after a while, it explodes. Goes to a really large value. So yeah, choosing your learning rate is it's a little tricky situation. It's choosing an optimal one is in itself a whole other thing, beyond the scope of this workshop, obviously. But yeah, keep in mind, you can't just put in a really large learning rate and expect things to work. So yeah, I try to go through this as quickly as possible. So if things are confusing, don't hesitate to stay back after the workshop, or if you have any quick questions right now, go ahead and ask them. But we should start off with what we want to do in this workshop, which is actually implementing all these functions that we've defined. But yeah, real quick before we do that, are there any questions? I see one. For comparison of the effect of different learning rates, shouldn't all parameters be initialized to the same value, like small, large, W, and beta are 0 at first, but the intermediate is allowed to be random? Intermediate is allowed to be random. What do you mean by the intermediate? We do our small and large W's and B's are initially assigned to 0, as you can see over here, before we call the gradient descent algorithm on them. I'm a little unsure about what intermediate is.
I think he means that the value we used before, the previous learning rate was random. Sorry, not the previous learning rate, the previous W and B. So the original one we defined way back when, that's our medium learning rate. But
right, yeah,
it shouldn't really matter too much in this case.
Yeah, yeah. So it's. I mean, you could also assign them randomly, but in a way, taking 0 is almost as good as taking a random. Not exactly true, but it works out in the way we want to. So yeah. Do we reduce the learning rate over time? No, the learning rate stays constant at one particular value that we assign initially when we call the gradient descent function. It does not change over time, no. Okay. Okay, if there are no more questions, we will look at a real life example first. But yeah, before but yeah, if you have any questions, guys, stay back after the workshop's over. If you are confused about any particular aspects of the functions, stay back. We'll go to them over you. We'll go to them again with you, and we'll hopefully be able to clear up any doubts that you might have. Okay. All right, so let's first do a real life example. So we have a CSV file in our GitHub for beginner track. If you go to workshop 8, as I am over here. Beginner trackball workshop 8. I believe our GitHub is linked in the forum, so just head on over there if you want to get that. But what we want to do is we want to grab this SAT versus GPA data set. What we want to do is we want to open it in raw. And once we do that, we essentially get a CSV file in raw, and we want to copy this URL. And once we do that, copy the URL, head on over here and paste it. We're gonna get our data set from here essentially. So yeah, and then we will call data is equal to pd.read underscore CSV, and then you just pass in our URL in there, and that's essentially just gonna take our data, taking the data from that CSV file, put it into a data frame, a pandas data frame. And if you look at data right here, as you can see, it's has 84 rows, 2 columns for SAT and GPA, which are basically the GPA value one would expect to get when you get like some SAT value. So yeah, that's that. Pretty simple. If anyone has any questions, let us know. But yeah, it shouldn't be too hard. So next thing first, let's just take a look at the data we have. So we can call the describe function on the data frame. And once we do that, you can take a look at some of the information that we have here. So we can see that our minimum and maximum values are in this range. So when we want to plot our points on a graph, we might as well use these as the bounds for our graph, which also you have to do in a bit. Can you scroll up one cell real quick? For sure, dude. Right here. Yep, no problem. Yeah, so grab the URL, put it into pd.read CSV, and just call data to take a look at how your data looks. Yeah, all right. So next steps, we want to extract only the SAT and the GPA values. We want to stuff them into a NumPy array, and the way we do that is SAT equals np.array, and we just call data SAT. So that will take the SAT column from our data, feed that into an NP array to initialize it as a NumPy array, and then stuff it in a variable SAT. And you can do the exact same thing with the GPA column. So go ahead and do that and that. And just for a sanity check, we can take a look at what SAT looks like. And as you can see, it's an array, whole bunch of values. And yeah, specifically 84 values. Cool, all right. Anyone has questions? Say it out now before we move on. And yeah, if you're still unsure about where to find the link for the CSV file, check out the Zoom chat. Jenson has kindly posted the link there. Okay. So next, can you go? Yeah, sure, no problem. I didn't really do much here, so the whole initialization process right here. Get a URL, feed into read underscore CSV, and then I call describe on it to take a look at a few things, and we kind of stuff them in these two variables, SAT and GPA. So yeah, hope that was enough time to look at things, Adam. What modules are imported at the top? I was away from my computer. All right, yeah. So if you scroll all the way back to the top, we have numpy is np, pandas is pd, and matplotlib.pyplot is plt. You should have already had these when you load it in the notebook. If you're running into an error, make sure you run all the cells before adding any new things, because a lot of the things we're doing is dependent on all these functions that we've worked on before. So if you're getting an error, and this is for pretty much everyone, if you're getting an error, don't forget to run all the cells. You can do that by going to runtime and run all. And that will essentially run all your cells together, and that's going to run the cell where you import your libraries, where you define all your functions, pretty much everything. It's key, don't forget to do that. So yeah. Yeah, so let's go ahead and plot our data on a graph. So we can kind of take a better look at what we're doing here. So we're gonna go ahead and do this. We want to do another scatter plot. SAT against GPA. Alpha here has nothing to do with learning rate. Don't worry about it. That's just one of the things that we have as a parameter into pyplot, matplotlib. Don't worry about it. X label. Hopefully most of the things, yes, as Jenson said, alpha is the transparency, it's not the learning rate, don't worry about it. I hope most of the things that I'm typing out on the screen, we've not really formally covered it. We're using a graphing library called matplotlib. Essentially what I'm doing here is I'm setting up the graph with our values, SAT against GPA, and then we're setting a title, X label, Y label, and then our X limit as well as our Y limits. And then finally we call plt.show to kind of run everything. So that's how our data points look. If you don't completely understand all these functions, don't worry about it. The main thing we want to do is kind of look at the data and see what we're dealing with. So as you can see here, we are seeing a fairly almost proportional sort of relationship here. As you can see, in a general case, as you score higher on your SAT, you also tend to score higher on your GPA. So that's the sort of function that we expect our model to essentially learn, a sort of straight line right through here, which kind of traces the data points. So let's go ahead and try to do that. So we first want to get our the number of data points we have, which is n equals SAT dot shape 0, and running that quick sanity check. That will give us, oh, sorry, I see someone said, can you scroll up? I'm sorry if I saw that a little bit too late, but these were the last two cells we ran. Yeah, so all this code will be posted, don't worry about it. You'll get a chance to tinker with them when you can. So yeah. All right, cool. Yeah, let's continue. We got n, which is the number of points we have, which we knew was 84, but we just we call se.shape0 to get it as in terms of the dimensions of n, in terms of dimensions of SAT. Cool. All right. So now we do some more initialization stuff. We call SAT.reshape which is going to be 1, comma n, because as you can remember, we were using row vectors for our algorithm for gradient descent algorithm, and we need to replicate the same thing over here. So as you can see here, if we call x, it's an array within an array, which is essentially saying it's a row vector instead of a column vector, and all of these are going to be in a single row. So yeah. Next things, we go ahead.
Wait, really quick question.
Go for it.
So, why did we define that n at the top? I guess I'm just a little bit confused why we had to define n as the SAT.shape before we did the x and y.
Yeah. All right. So let's see if we can get from here. Yeah. So as you can see, our SAT array as we got here is essentially a column vector. It's a column vector which has 84 rows and 1 column in it. That 84 rows corresponds to essentially the number of data points that we have, which is our n value. In a lot of the cases where we use n, like over here, for example, n here or n here, that's our n value. That's the number of training points or the number of training samples that we have. We want to get that. And even though we know we have 84 points here, as you can see here, we have a count of 84. In a lot of cases, we might not end up doing this. So we know for a fact that since our SAT is a column vector and the number of rows in that column vector corresponds to the number of data points we have, we can just tap into the number of rows for that column vector. And we do that by doing SAT.shape 0. If we did SAT.shape 1, yeah, if we did SAT.shape 1, for example, that would give us, apparently that doesn't work. I'm not sure why. Either way, we want to tap into the dimensions.
There's only one column so that it can't access anything outside of it?
Okay, I'm not really sure, but this is supposed to, if we do 1, it's supposed to, I think it's supposed to return 1 because it should tap into the fact that there's only 1 column, but I'm not too sure what it.
So it's a weird thing about NumPy that if you just define a vector using only one dimension, it gives you something called an ND array. It doesn't really give you a two-dimensional matrix. So it'll give you 84, 0, 84, none, as a lot of people are pointing out. So it's this weird type, and actually that's a kind of a thing to keep in mind is specifically define your types like we're doing in the reshape line, which you can run into errors if you have this 84, nothing. But yeah.
Yeah, actually, I actually completely forgot about that because we ran into the same issue in the previous workshop as well, where we were getting a whole bunch of errors, and the reason for that was of this weird sort of definition of the dimensions for a row vector or a column vector. So unless you explicitly assign it like we did over here, we're saying like x is 1, n. We know for a fact that x will have 1 row and columns for sure, not like this whole 84, none stuff.
Okay,
but yeah,
that makes sense.
yeah, n SAT.shape 0 gets us the number of data points we have essentially. So yeah.
So is that also, is that similar to transposing it? Or...
I mean, yeah, I mean, this reshape here, I guess, is essentially transposing it. Transposes, yeah, okay, yeah. So yeah, you have a column vector, and then when you apply the transpose, you get a row vector. So yeah, essentially transposing it. Pretty much. So
okay,
yeah. So yeah, the next step right now, and since we have a lot to do today, I'm gonna go to these fairly quick. Again, we wanna randomly initialize our weights and bias. So we do 1, 1. Then we do b is equal to np dot I know how to spell. random.randn, again, 1, 1. And for sanity check, let's check what W is. As you can see, it's a value randomly assigned. Probably is not the right weight we want for our model. So yeah, let's go ahead and call gradient descent. That's like the big thing we want to do. So we do WB and losses. Because if you remember, our gradient descent function returns 3 values in this order: the final weight, the final bias, and an array of all our losses. So we're going to go ahead and call gradient descent. And we pass an x, comma y, which is our input and our labels. This is a little weird. We assign a very specific learning rate. And the reason for this is when you're making this example, we tried some learning rates. This is the one that worked best. Again, choosing an optimal learning rate is a whole thing in itself. But if you want, once you get a chance and grab this notebook or the notebook you're working on, tinker around with the learning rates, you'll see that sometimes certain learning rates may not work. So yeah, we have a very specific learning rate, and then we assign W and B. Yeah, Jenson, go ahead, add what do you need to say.
So for this data set in particular, because our X is our SAT score, which is from 1600 to 2400, and our Y is GPA, which is from 0 to 4. So as you can probably tell, the actual slope of the regression line will be like extremely small. So that's why we need a really small learning rate as well. So that's just some like intuitive like background behind like why the learning rate is so small.
Yeah, yep, exactly. So yeah, learning rates, fun stuff. All right, so we call our gradient descent algorithm just like this: X, Y, learning rate, weights, and bias. And for sanity check, let's run our W, and we see we get a different weight. And we expect this weight to be the right one. So yeah, let's see. So what we want to do right now is we want to once again plot a lot of things. So we want to plot this exact same thing again. So I'm just gonna go ahead, copy these because we've already done with it, and I don't want to write them all out again. And now we're going to do a little bit more. We want to plot our actual values that we learned, our actual line that we learned. So we go ahead, once again, initialize a bunch of randomly, well, not random, but like for a whole bunch of testing points, I guess you could say. We want it to be between 1,600, 2,100, and we call num equals 500. So we're getting 500 data points between 1,600, 2,100. And that's gonna be what we feed into our y hat function here, which if you remember is wx into b. So we once again do wbx plt.scatter to begin plotting stuff down. So we do x, comma y, comma color is equal to r, and alpha is equal to 0.2. Yeah, and once you do plt.show, fantastic. So what we can see here is we've produced a line that in its best attempt has created a function that helps us guesstimate the GPA one would get using for some particular SAT value. And as you can see, as I said before, we would expect it to kind of pass through something similar to here, because we can see a pretty proportional-ish relationship. So yeah, I think that's about it. from me here for this very simple example of linear regression with just one unknown in this case. So once we move on to whoever's next, are there any other questions? If you have any other questions, please ask them out now or stay back after the lecture because we have a lot of stuff to do today. Don't hesitate to stay back after, not the lecture. Why am I keep saying lecture? The workshop, and then we will deal with it. We will deal with the questions then. Yeah. So I see questions. That's the plotting functions, plotting commands. So yeah, that's it from me. Jenson, take it away.
Yeah, so before we move on, I just want to say, like, I know like we're gonna cover a lot of stuff in this workshop, so we're gonna be hosting an office hours this week on Thursday, 9 p.m. PST, I believe. So like feel free to show up. I think at least like 2 of us will be there. So yeah, if you have any like further questions regarding to our code, then feel free to go to office hours. We'll be happy to help you out. I'm gonna share screen. All right, can you guys all see my screen? All right, so we have prepared a worksheet for you guys for this workshop, and I believe it should be linked in the Google form. So I'm gonna give you guys like a minute to open it and make a copy in your drive. Yeah, thank you, Sudhanshu, for reposting the link. If you don't see the link to the worksheet, feel free to just refresh, because I think I added the link a little late. So if you open the feedback form like right at the beginning of the workshop, the link might not be there. I guess feel free to like react when you guys have the worksheet open. All right, I'm seeing some reactions, so I'm just gonna, I guess, move on. All right, so for this particular worksheet, we're gonna work with a data set that is slightly more complicated than the ones that we've been working with, applying the knowledge that we learned in the process. So we're just gonna import some modules at the beginning, just like we did before. I'm just gonna wait for this to run. All right, it should be run. All right, so the data set that we're gonna use for this worksheet will be load Boston. I'm sure some of you guys may have heard or worked with it before, but this data set is from the module scikit-learn.datasets, and we're just gonna import it with this line, and we're just storing it into a variable called Boston dataset so we can access it easily later. All right. So after that, so this dataset has like some attributes that we can explore, and one of it is the documentation, which I think is pretty interesting. So I guess the most important takeaway from the documentation is the number of training samples is 506, and we're working with 13, I guess, features. And I think most of them are numerical. I think there's one that's called the Charles River dummy variable that's actually categorical. So I think if the particular house is near a river or the Charles River, it'll be represented by a 1, and if it's, I guess, further than a certain like distance, then it'll be represented with a 0. I thought this is kind of interesting, and I guess you guys can like feel free to read the documentation to learn more about what all of these features actually mean, because they're actually quite interesting. And yeah, there's also like some information here about the author or whoever made this data set. So I guess there are also like some other attributes of this data set as actually like quite useful. So I'm just gonna go through them real quick. So the first one is Boston dataset.data, which pretty much contains all the data in this data set. And let's just verify the shape. So it's 500 by 13, which is as expected because we have 506 training samples and 13 attributes. And another useful attribute of this data set is, I think, the target. Yeah, so this is basically an array that, a NumPy array that stores all the labels for this data set. So the shape is, yeah, 506 by none. So that's also as expected because we have 506 training samples, and each sample has a label. And the last feature that's going to be useful for us is the feature names, which is basically an array that stores all the name of the features that we're going to be using. All right. I'm going to pause for questions if there's any. Feel free to unmute. I guess if everyone is like, if everyone is good, then I'm just going to move on. All right, so the next step is just putting this Boston data set into a data frame object using the Boston dataset.data as the data in this data frame. And the names of columns will just be the feature names. So I guess we can just do a sanity check with data.head. All right, so yeah, as you can see, the indexes in the row-wise indexes are just the number, like the feature or the training sample numbers, and the name of the columns is just the name of all the features. And yeah, I think this definitely makes a lot of sense to me. Like the data frame object is as we expected. And then let's just do a quick data cleaning step to check if there's any missing values. So as you can see, like everything here is false. So that means we don't have any missing values. So that's really good news. I know the documentation says there's no missing attribute values, but I guess if you're working with like a data set that you've found online randomly, then it's always a good idea to check where there's missing value, because that is definitely going to affect how your model performs. So the next step before we can start training our model is to split our training and data set from our testing data set. And we're going to train our model with only the training data set. And we're going to be using the 80:20 ratio, roughly. So we can do this by slicing the data frame here with data.iloc. And we can verify the shape of xtrain. So there are 400 training samples, and xtest has 106. So that's roughly an 80:20 ratio between the training and testing. And we can also slice the labels accordingly. And I guess we can verify the shape of ytrain and ytest as well. Oh wait, shape. So ytrain has shape 400 by none, and y test shape 106 by none. So like we did before, we're just gonna reshape y train and y test to 1 by 400 and 1 by 106. And we're just gonna initialize the weights and biases randomly like we did. But this time the weights is 1 by 13, where 1 by n, where n is the number of features. So that will be 13. So we can just, I guess, once again, verify the shape of W. Yeah, it's 1 by 13, where 13 is just the number of features that we have. All right, I'm gonna once again pause for any questions. Feel free to unmute or type in chat.
So I know for now that just using the random weights work, but like in like future projects when things get more complicated, do you still just initialize the weights and biases randomly, or is there another way to do it?
Actually, I think like initializing the weights randomly will probably work best, because especially if a lot of weights and biases, because like for a model that's like as complicated as this, like there are definitely like multiple local minimums. So if you like have a different starting point, you might end up you might converge at a different local minimum with your gradient descent. So it's definitely a good idea to like run the gradient descent multiple times with different like starting points, and just pick the one that ends up with the lowest loss, because that's most likely to be the global minimum for the loss function.
Okay.
But I guess for the example that we went through with like two, one weight and one bias, it's okay to initialize it at 0, because there's only like one local minimum. So we're guaranteed to converge towards the same one.
Okay, that makes sense. So like with something like this, it's almost inevitable that you're gonna land within some local minimum or something like
Yeah,
that.
there are definitely going to be
okay.
multiple. So
Got it. Okay, thank you.
Yep, no problem. All right. So those are really good questions. So the challenge for this worksheet is implementing like all these functions by yourself. Y hat, which is okay, we've implemented MSD for you because it's the same like for two variables and like 13 variables. But the challenge here is to implement Y hat, gradients, and gradient descent using the knowledge that we learned in the workshop. And in principle, this should be pretty similar to what we did, but there are some like slight differences because we are working with like, I guess, more features. And I guess we've provided the code for visualizing some of the losses. And we also gave you a learning rate that you can, I guess, explore a little bit. Okay, so if you have to write this much code like every time I want to do like linear regression, that'll be kind of tedious, not gonna lie. So luckily we don't have to write this much code because scikit-learn has got our back. So yeah, so we can just import linear regression from scikit-learn.linear model and the function train test split from scikit-learn.model selection. So I'm just gonna run the cell, and then I'm just gonna store the data into this variable called x and the targets into a variable called y. And then I'm gonna call this train test split function, providing our inputs, our labels. The test size here is just the training and testing data set ratio. So 0.2 here means I want 20% of our entire data set as the testing data set. And so the trained data set will be 80%. And the random state here is just, I guess, a random seed. Because like essentially how this train test split works is we're splitting our train and testing data set randomly, and then the random seed is just, I guess, specifying how this is going to be done. So if you use the same random state, you'll end up with the same training and testing data sets. And as you can see, the shape is quite similar to what we have above, but I guess it's 404 instead of 400 because I didn't actually use the 80-20 ratio like precisely. It was just a rough estimate. And now time for some scikit-learn magic. So we can actually just run linear regression with this one line. So we're fitting our linear regression model with only the training data set here. And then we can look at our weights and bias with regression.coef underscore, which is kind of weird syntax, but this is just how it's done. And same for the intercept. And then we can also evaluate how well our model performs with this R2 score, which is the coefficient of determination. So an R2 of 1 means the model perfectly fits the data. And I think an R2 of 0 is just like probably just like a straight a line with constant value. So no matter what the input is, you always predict the same value. I think that would end up with a R2 score of 0, unless your data set is just constant. And we can make our predictions with our testing data set here with regression.predict, and we're just gonna store the predictions in this variable called ypred. And then we can compute the R2 score by setting ytrue to be ytest, which is the labels, and ypred to be our predictions. And our R2 score is 0.73, which is not terrible considering we only have 404 training data sets. And as you can tell, we have 13 features, so this data set is actually like quite complicated. So yeah, I think 0.73 is a decent value considering like we only have a small amount of data. So in principle, if you have a larger data set, this R2 score will most likely be larger. So like closer to like 0.9. But now like our R2 score is only 0.73. All right, seems like we have some questions. What is the target again? The target is just Boston dataset dot target. And, oh, okay, it's already answered. Can you scroll back up to the y hat Boston var def? Oh, you mean the function? Yeah, so this is just a challenge for you guys to, I guess, implement the gradient descent for this data set. And like, here we're just plotting the losses like we did before. So if your losses decreases towards 0, then that means your model is doing a good job. How many epoch does linear regression .fit run for? That is actually a good question. I don't know this on top of my head, but I'm assuming like it just stops when the loss is lower than a certain value. It'll run until it converges. Okay, yeah. Okay, any more questions? If not, I'm just gonna pass it to Sudhanshu, who's gonna go through the logistic regression part of the workshop. Okay, yeah.
Okay, cool.
Sudhanshu, you want to take over?
Yeah, can everyone see my screen? The one with the one cell on it?
Yes.
Cool. Okay, so I'm going to give you all a minute here. Just open up a fresh notebook. So we say File, New Notebook, and have these 3 lines. So consider this like a couple of minute, 2-minute break, and ask any questions in the meantime. But just have this notebook with these 3 lines of code ready. Tyler, we have the feedback form / link tree, which contains the link to the worksheets as well as to the notebooks, as well as to the GitHub. Let's check that out. Okay. Once you guys have this ready, if you could give me some indication, that would be really helpful. Okay. I'm going to assume that everyone could open File, New Notebook, and have these 3 lines of code. So we can get started. And basically, the objective of this notebook, right, is to implement logistic regression, which is implement a classification problem. And it's going to look really, really similar to what we did in linear regression. So I'm mainly going to be focusing on the parts that are really different and really specific to logistic regression. So you're going to see a lot of this same stuff we did before. So I'm going to start off by defining some kind of a data set. And let's say my sigmoid as a function of x is simply f is equal to 1 over 1 plus np.exp minus 2 times x minus 1. And we return f. Okay, so what I've basically done here is I've defined some really arbitrary function that we're trying to learn. So in particular, the w is 2 and the b is minus 1. And if you want, you could feel free to change this value and try learning a different function. It'll work just as well. But this is what the function I've decided to learn is. And now let's construct the data, like similar how we did it last time. So I'm going to say m is equal to 500, the number of data points. X is equal to np.linspace minus 5 to 5, num is equal to m. That means 500 linearly spaced data points between minus 5 and 5. Exactly how we did before. And I'm also going to reshape it so that everything is kosher. And then I need to get my y values, which is my labels. So the way I'm going to do that, I'm going to call my sigmoid of x, and that'll give me all of the corresponding y values. And again, let me reshape that. And just for good measure, let's do a scatter plot of this to kind of visualize what our data looks like. As you can see, we got a pretty nice sigmoid function over here. And further, what we need to do is kind of classify this into 2 categories, either 0 or 1. If you remember from the theory workshops, that's what we do. So if we have a value that's greater than 0.5, we want to classify it as a 1. Similarly, if you have a value that's lesser than 0.5, we want to classify it as a 0. So I'm going to paste a quick to-do cell over here. Just read over this. So essentially, what we want to do, sorry, I saw a scroll up real quick. Yes, I can do that. So yeah, so we just defined an arbitrary function. I've decided my parameters are 2 and minus 1 because I guess today we're in December now, so 1 and 2. But this is a completely arbitrary choice. And then I just create my training data. And by visualizing it, we get this nice sigmoid curve. Okay. So now we need to classify the data. So we need to bucket it into either 1 or 0. And the way we do that is if a value is greater than 0.5, labeled as 1, if it's less than 0.5, labeled as 0. we need to go over each and every y value and do this for each of them. So of course we could do this with a for loop, but if you remember from my NumPy workshop, there's actually a pretty clever way to do this using just one line of code. And does anyone have any idea what that could be? You can type out in the chat, that would be really nice. Okay, I just want to reiterate, it's just figuring out whether y is greater than 0.5 or less than 0.5. Does anyone want to take a guess? All right, if not, the line of code is essentially just this. Y is equal to y greater than 0.5. And that will do, okay, yeah, so someone messaged me in private, and yes, that's exactly right. We just do y greater than 0.5. Also, so let me go ahead and try and plot my new y values. So I'm going to say scatter x comma y. So as you can see, we have these two distinct classes here. Yeah, absolutely. So, so someone mentioned that gives us true and false. Yes, but as we know, true corresponds to 1 and false corresponds to 0. So NumPy automatically recognizes that and gives us ones and zeros. So that's something that's done completely implicitly. And it works that way in most languages. So if you typecast a false or a true to integer, it gives you 1 or a 0. So this is what our training data is. Now I want to point something out. Now what we need to do is build our model based on this data. And in a real world machine learning application, like we did in linear regression, all of this stuff doesn't exist. What happens is we're given some x and some y, and we need to work with that. So let's assume for a second, all this previous stuff never happened. We have no idea this w is 2, this b is -1, none of that happened. We've been given some x and some y. I'm going to try and find the function that fits it. So I need to try and explore this data set. So I don't know, maybe a plot would be helpful. Let's see. Okay, wow. I mean, I've never seen this before, right? And it looks to me like there are two distinct classes, and they seem to be separated by some boundary here. I don't know about you guys, but I mean, I've never seen this before. Maybe a sigmoid function would work really well. And I know I'm sounding a little silly right now, but this is exactly how you would probably reason through a project like this. You'd look at the data and kind of figure out what the model should look like. So I've decided that my model, my hypothesis, is going to be a sigmoid function. So I quickly look up the formula for what that is, which is this 1 over 1 plus e to the negative wx plus b. So here my parameters are w and b. So let's try and implement this in NumPy. So we say def y hat as a function of w, b, and x. And I need to simply code up this function. So again, yeah, so can anyone think of how we could implement this function in NumPy? It's similar to a lot of the stuff we did in the NumPy workshop, and it should be just one line of code. And like, don't worry about getting the answer wrong. You can also message me in private, or just feel free to think out loud in the chat. Yeah, good stuff. That's exactly right. So we just say, let's say f is equal to 1 over, oh wow, okay. Okay, great, that's really awesome. A lot of you got it right. 1 over 1 plus np.exp of minus w times x plus b. So literally how you would read out this formula is how you would type it out. That's the kind of the beauty of NumPy. It's exactly what you'd expect it to be. So let's keep that. And now let's initialize our weights. So we say W is equal to 0 and B is equal to 0. I mean, you could do it randomly. We could do it with this. It's all good. Don't worry about it for this particular problem. Okay. So yeah, let me pause here. Does anyone have any questions about what we just did? And remember, all we've been given is this set of data, zeros and ones in some particular order. Okay. Okay. I think we're good, but otherwise, always feel free to type it on the chat. Now, if you recall, once we have our data and our model, that is our hypothesis, the next thing we need is some sort of error measure, some sort of loss function. And does anyone remember what the name of the loss function was for logistic regression? It had a couple of names, either is fine. So if anyone wants to answer that, okay, I see one of the names. Does anyone know what the other name is? You're close. You've kind of combined the two in an interesting way, but you're very, very close to the right answer. Yeah, okay, perfect. So we have two names. One is binary cross entropy, and the other is log loss. And log loss is a little more commonly used, but binary cross entropy sounds really cool. Okay, and of course, binary cross entropy is this kind of monstrous formula that you see over here. And it looks really scary, but it's actually not as difficult to implement as you might think. So let's go ahead and try and implement this. So we say def log loss y and y pred. Oops, y pred. So y is the y over here, and y pred is simply our y hat term, our predictions. So now again, I'm going to pause, right? And our objective is essentially to implement this function here. And once again, we can do it with the for loop. We can do everything in life with the for loop. But NumPy allows us to do this in one line of code, which will probably be a lot faster. And the line of code isn't completely obvious at first glance. So I'm going to give you all a minute here to try and pause and think about how you might implement this. And like, don't worry if you don't get it, because it definitely takes a second to think about. So remember, we have an average going on, we have a log going on, we have the subtraction going on. There's a whole lot of stuff going on. So take a minute and try and think of it. And obviously try and think out loud in the chat as well. So that we can help you if you think of it. Okay. Does anyone have any preliminary thoughts about how we might go about doing this? Multiple logs can be combined, right? I'm not 100% sure what you mean by that, but we can take the log of an entire array, if that's what you're asking, all at once. Yeah, that's a good intuition. Or we can definitely use np.sum, and that'll be useful for the sigma over here. And someone's mentioned, oh yeah, okay, so that's definitely true, that multiple logs would be combined. So if you can find a way to use that, that's also really helpful. And yeah, I want to point out that the implementation I'm going to show you is just something I came up with. There's probably 100 different ways to do this just as well. Does anyone have any other thoughts? This is really good. Definitely try and reason through a problem like this. wow. Okay, let's see. Return negative n. Okay, I'm not going to read this out because it's pretty long. np.log of y hat plus 1 minus y log of 1 minus y hat. Yes. So I think a lot of you are on the same track, and that's really great. Yeah. So I see one of you. I'm not going to call you out, but you missed a negative sign. So that's something to keep in mind. There's an overall negative sign over here, but a lot of good answers. Okay, exactly. So you've realized that as well. But a lot of, yeah, looks really good. I think all of you are on the right track. I'm just going to show you my implementation for it as well, because why not? But all of those will probably work just as well. np.sum, np.log, np.abs of y pred minus 1 plus y. And that's just my implementation of it. I don't know why I think of doing it this way, but that's what it is. But all of your implementations are going to work just as well, and they're just as good. So yeah, if anyone else is worried about it, just feel free to copy paste one of those things you see in the chat, because they're all really, really good answers. Okay. And let me give you a demo of how we're going to use these functions we just defined. So if I want my predicted values, I'm going to take my y hat function, my w, b, and x, and output something. Similarly, if I want to call my log loss, I take my true labels, y, and my predictions, and I calculate some value. So this value happens to be 0.693147, whatever, some arbitrary random initial value. And the next thing, so now we have our data, our model, our loss function. We need gradients. That's the next step. So we need gradients with respect to W and B. And surprisingly enough, it's going to be exactly the same as what we did in linear regression. So I'm going to kind of blaze through this part because it's going to be the exact same code. You can literally copy paste parts of the code you have from the previous workshop. So I'm going to say m is equal to y underscore pred dot shape of 1. So this is just an intermediate value. Don't worry about it too much. Y pred minus y. Grads is this empty dictionary. Grads of db is equal to 1 over m of mp.sum dz. Grads of dw is equal to 1 over m np.dot x comma dz dot transpose comma 0, and we return grads. Okay, so I'm going to walk through what I've done here. So I've just said that m, the number of training samples, is the second dimension of y, very similar to how we did last time. dz is just some intermediate value. The significance is a little more involved, but think of it as just some intermediate value that's going to help me out later. So I just define it to be y pred minus y. And grads, my gradient dictionary, is initialized to be this empty dictionary. And I initialize each of the gradients with respect to b and w to be these values over here. And this is a little annoying because this returns a matrix, but all I want is a scalar. So I need to extract the first column and the first row. It's kind of a hack, and it's only because we're doing this single variable case. In the multi-dimensional case, you don't have to do all this. By the way, the implementation I've done here is a little bit of a hint for how you might think about doing the worksheet. Okay, let me pause here so that you all can catch up on this bit of code and also see if you have any questions. Okay. If there are no questions, I'm going to move on to the next cell. So the next cell is not something you need to implement. It's just something that I wrote up to kind of visualize this model. So let me just copy paste this bit of code, again, like I said, don't worry about not implementing this yourself. You can look at the code later on. But all I've done is plotted my predictions, my current predictions with this this model I have with, where is my W and B? Where is W and B? Yeah, with W and B equal to 0. So it's our initial guess. And as you can see, it's pretty terrible. It's literally a straight line when we're looking for a curved line over here. And the accuracy is also really terrible. It's like 55%. I mean, this model is not going to get into UCLA. So we need to do better than this, right? And to do that, we're going to start doing gradient descent, the old reliable. So let's say the training routine is, let's call it def run gradient descent. So this is a function that takes in x, y, parameters, a max number of iterations, and a learning rate. Okay, so let me walk through what this prototype is saying. Give me an x, give me a y, give me some parameters. In this case, that's w and b. Give me a maximum number of iterations, and give me a learning rate. And I'll give you gradient descent. So a really good practice is to do the following. So when you have a function, define what each of these variables actually means. So x is an array of size 1, m. These are all in comment entries. And y is an array of size 1, m as well. The max number of iterations is simply an integer. And the learning rate is a float. So of course, this is all not necessary for your model to work fine, but it's really good practice, and it makes your code really clean, really readable, and anyone implementing it later in the future, including yourself, will really understand what it means. Okay. So, oh wait, one more thing. So the params is a dictionary. It's a dictionary such that params of W is the W value, and params of B is the B value. So what I've done is I've kind of taken the code we had before and kind of formalized it a little bit, because we only have two parameters, W and B, but we could, in theory, have any number of parameters, like 10,000 parameters. So I'm going to wrap them all really nicely in this dictionary and kind of pass them all in a dictionary. Otherwise, you're going to have, parameter 1, parameter 2, parameter 3, parameter 4, all the way up to parameter like 10,000 passing through this function. This is just a cleaner way to do that. Okay. And I'm going to say for I in range max iter. So I'm going to loop over the max number of iterations. And I'm going to say y pred is, of course, y hat, w, b, and x. So I take my w, I take my b, and I get an x. And yeah, someone mentioned me in private that we could also use a doc string, and that's absolutely true. That's also a good convention. I've just put it in comment entries for now, but that's something you can explore as well. Okay, so now that we have our predictions, let's get our gradients. So let's say grads is get grads of w, b, x, y pred, and y. So this is the function we defined earlier. If you're wondering why this looks a little mysterious, it's just exactly the function we defined earlier, and it depends on how you've defined it. Yeah, Jenson's mentioned in the chat that max iter is also known as the maximum number of epochs. So that's true as well. Question: wouldn't you need to pass params of W into y hat in the same W and B? Oh yeah, you're absolutely right. That's actually my bad, everyone. So I've defined over here that my parameter dictionary consists of W and B, but I forgot to actually extract the values. So let me go ahead and do that. So I extract W and I extract B. So yeah, thank you so much, Adam, for pointing that out. That is my bad. We just need to extract the values W and B from our parameter dictionary. And once we get our W and B, we pass them into our Y hat. Okay. So now that we have our gradients, the gradients are also in the form of, where does it come? Form of this dictionary over here. So we need to try and extract the gradients dB and dW. The way we do that in Python, of course, similar to how we did it over here, is we say dW is simply grads of dW, and dB is grads of dB. So we just extract the values we just are computed. Okay. Now the next thing is gradient descent. So we need to take our B, we take our W, and we need to update them. And I know I feel like I'm patronizing guys, but what do you think the formula for this is? Because gradient descent is kind of the crux of this entire workshop series. And it's, if you want to remember one thing from this workshop series, is the formula for gradient descent. So you need to take your learning rate, your gradient, your parameter, and update it. So if anyone has the answer, how would I update these parameters? Right, absolutely, it's the same equation. Does anyone want to type out the NumPy code for what it is? Yep, absolutely. So a lot of you got it right. That's completely true. So we just take our old B, we subtract learning rate times dB. Similarly, we take our old W and subtract learning rate times dW. So this is gradient descent. And I know it seems silly to keep hammering on this, but this is kind of the crux of this entire workshop series. And it's a really, really important concept. Okay. And like before, what I'm going to do real quick is just compute the loss. So I take my predictions and my actual value, and I'm going to append it to some list. So this is going to help me track what the values are. And it's giving me a nice visualization later on. And at the end of the function, I return my new, brand new, updated W and B. So this is your gradient descent function. Let me pause here. Does anyone have any questions about anything we just implemented? Could you show get grads? Okay. Yeah, here you go. And I see that the next question is that where do we define losses? And yeah, that's a good point. So I'm going to define losses later on globally, but you could also define it locally and return it like we did last time. So you'll see that in the next cell where we define losses. Yeah, and I hope this is the get gradients function where we compute the gradients, put it in this dictionary, and call the key dB and dW. Okay, cool. So now, like someone mentioned in the chat, I'm going to make a losses list. So I'm going to say losses is equal to empty list. Now I'm going to initialize my params. And like I mentioned here, I want my parameters to be a dictionary. So I'm going to say params is equal to W initialized to 0 and B initialized to 0. So this is a nice clean way to have all my parameters hashed by these keys. And I definitely recommend doing this if you're trying to implement it yourself. Now I need to run gradient descent. And let me type that out. Okay. So what we need to do is we pass in the X we defined way back when, pass in the Y, pass in this parameters dictionary, pass in a number of iterations, and pass in a learning rate. And that returns a W and a B which are updated. And I'm going to go ahead and try and plot what we've just done. So I get my brand new predictions using these improved W's and B's. So that's what I pass into this function over here. And I'm going to scatter this new predicted list. So again, don't worry about this plotting code. You can probably copy it down later because it definitely takes a couple of seconds to parse all of the arguments we're passing through. And legend. There's a bug, get grads is not defined. Why is it not defined? Maybe I didn't run the cell. Huh, okay, sorry. Apparently I didn't run the cell before. That's just a silly thing to do. Okay. But yeah, okay, so you can see the function has begun to learn what this looks like. But I have a strong feeling that this learning rate is a bit too high. So let me try, I don't know, maybe 0.2. Okay, so that looks a lot better. As you can see, it's kind of coming closer and closer to what this true value actually is. So the orange is the true labels, and the blue are our predictions. Let me try increasing it. Oh, I'm sorry. Go ahead.
Oh, I was wondering. So how did you know that the learning rate was too high there? Is there a way to tell?
Yeah. So that's just a suspicion, right? So it could be a whole number of things. It could be that my training data is bad. It could be that the number of iterations is too less. But usually like the data is not something you can change. That's what's given to you in the problem. And max iterations sometimes depends on your like computational budget. So the real parameter that you can play around with is your learning rate. And that's kind of one of the most powerful tools. So that's something I tried. Yeah.
Okay. Thank you.
Absolutely. So yeah, so this is what my predictions look like currently, which is not bad at all. I can try maybe increasing it a little bit. Let's see if it does any better. It doesn't really. So we've probably reached a nice point over here where we get maybe learning rate of 0.1, 0.15, and that gives a pretty good model. So I'm also going to plot my losses. Oops, plt.plot losses, which is what I calculated earlier. And as you can see, it goes down really nicely. It starts off high and goes down to almost 0. So a quick way to plot something is just to say plt.plot and pass in an array. It's literally like three words. Okay. And next, so we have all these heuristics over here. We have that this curves kind of match. We have this loss goes down. It's kind of hand wavy. So we want to put a real number to how well our model is performed. And what I'm going to do is implement accuracy, or accuracy. So that's going to tell me how often has my model correctly predicted the right label. So if you recall, ypred is simply a list of all these decimal values. But that's not what we want. We want an exact label, 0 or 1. That's all we want. So again, we can use the old reliable trick and convert it to falses and trues. So false corresponds to 0, true corresponds to 1. And again, it really doesn't matter whether it's Boolean or integer. And now I want to take this list and compare it to my true labels. So if I run this line of code, every time I get a true, it's when my model correctly predicted the value. And every time I get a false, is when my model failed to predict the correct value. So it's, again, using NumPy broadcasting, it takes this list, and compares it element by element. Okay. And I can go even further. I can sum up all of these values divided by m and multiplied by 100. And that gives me the accuracy of my model. So it's just simply telling me what percentage of values are correctly predicted. And so this model is doing a lot better. It's like 91.4%. And if you remember, our old model was just 55%, which is pretty terrible. And so we've done a lot better. And I want to quickly point out one last thing. Actually, we can look at this plot itself. So you can see the model has learned these kind of boundaries really well, but it kind of breaks down in the middle over here. And that is, and the reason for that is kind of open-ended. But my own analysis of that is that this is a really steep ascent. So it's really difficult for the model to predict the exact values we need to find to kind of match this perfectly. And that's why it kind of breaks down. And there are a lot more advanced techniques that you can use to get this accuracy even higher, like 98% or whatever. But as a simple rudimentary model, this is done pretty well. I mean, it's predicted the right value 91.4% of the time. Okay, let me pause here again. Does anyone have any questions about this last section? Okay. Yeah, absolutely. Please fill out our feedback form. But yeah, if there are no other questions, I'm going to quickly switch over to these slides we have over here, because that's the end of the notebook for now. And before we leave you guys, we want to try and show you what you can do with all of the stuff you just learned, because we just threw a lot of concepts at you over the last 8 weeks, and we want to see like where can we take this. So these are some concluding thoughts. And firstly, thanks a lot. Like, it's been a long quarter for all of us, and we really appreciate you sticking it out with us. So to quickly review, the material we covered this quarter was gradient descent, kind of the fundamental algorithm of all of machine learning. Then we predicted continuous values using linear regression. We did classification using logistic regression, which is what we did in this workshop. We also studied another classification algorithm called k-nearest neighbors, which is really powerful if you have less data. Then we did scientific computing using NumPy and data analysis using pandas. And these libraries, like you saw in these workshops, are just used so often everywhere you go, that they're kind of really essential skills to have. And then we went ahead and implemented machine learning models from first principles. So we did a lot of really cool stuff. And what comes next? So all of the stuff we just did comes under the domain of shallow learning. That's kind of the colloquial term for it. It's different from the deep learning that you'll learn next quarter. And shallow learning, even though it doesn't sound as cool as deep learning, is actually really powerful. And there are some concepts like lasso, ridge, principal component analysis, linear discriminant analysis, and other stuff, which are like incredibly powerful. And in my own experience, they've sometimes worked better than like a fully fledged neural network. They're really powerful techniques. So don't dismiss them just because they don't sound as cool as neural networks. And a good Python library, like we mentioned before, is scikit-learn, which has all of these algorithms implemented for you. And next, like Vaishnavi mentioned, we're offering an advanced track workshop series in winter, where we're going to be talking about deep learning through neural networks. So it's the cutting edge stuff you've heard about in the news, and it's really cool stuff. And we'll be talking about models like classic neural networks, convolutional neural networks, which is the stuff that self-driving cars use, recurrent neural networks, which is pretty much what Alexa and Siri use. And we're also going to be offering another beginner track workshop next quarter. And I want to reiterate once more that since we're offering beginner track next quarter, we really appreciate your feedback. Like anything you think we did well, we did badly, we should change, like please let us know in the feedback form. I've linked it again in the chat. Please fill it out for us. And that's it. So that is the end of beginner track for fall quarter. Thank you all so much for coming. Again, feedback form on the slide, the attendance code, and follow us on Facebook, check out our GitHub page, hit us up on LinkedIn, Twitter. It's all good. We'd love to stay in touch with you guys after this as well. And yeah, feel free to stick around if you have any other questions. But that is the end of beginner track for fall 2020.
Also, a huge shout out to Sudhanshu, Jenson, and Adithya for putting on this track throughout the quarter. It's their first time teaching, and I think they did a wonderful job. And shout out to all of you guys for coming out.
Yeah, thanks a lot, Vaishnavi.
Thank you.
You're welcome.
Yep, it's our
Okay.
pleasure. It's nice to get to know you guys.
Yeah, it's really nice seeing you guys every week.
Yup, absolutely.
So I'm going to go ahead and stop the recording. Thanks to everyone watching as well.